Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. Today our topic is Fundamentals of Video Processing. So we discussed how images are represented earlier, but let us see how the videos are also represented. As you understand that videos are nothing but it is a sequence of frames. So we have in the case of video, we have it as a function of space and also time. So that's why we can represent a video as a three-dimensional function over space and time. Here space is the image space. So pixel locations are elements of those space, and at each location you have the respective brightness values, and it's a digital image as it is formed through the optical camera. But at every time, regular time instances, these frames are captured and this sequence makes a video. So from this diagram we can observe that how the dimensions are shown here. So this is we are showing as if this is a time dimension. So as we progresses with time, the frames are getting captured. So every frame has a time instance associated with that in this case, and every frame has is an image in other way. So and also this example shows that these are the images. So one of the features of this thing is that as it is a sequence of frames, so there will be a lot of temporal correlations between the frames. So this image and say this adjacent images, there will be many things which will be very much related or common. Many static objects, backgrounds, they may be common. So those are the characteristics which one should use for processing a video. One should keep into mind while processing a video. So for acquisition of video, we in the beginning, as we have as the technology moved, initially videos are captured as an analog signal, as a continuous signal over the time domain. So that is the analog capture, and that's why there is a requirement of converting this this frame over time as a sequence of samples and with certain format, with certain convention. These samples should be read so that we can get a two-dimensional frame out of those samples, and also we should get a sequence of frames from that time domain signal, time varying signal. So it shows that there are different kinds of formats like composite or component or S-video. These are different kinds of formats, and then finally there are standards by which the signals are represented. So video has become a time varying signal. It is so there are standards, as I mentioned. It should have several signaling information related to the interpretation of the frames and the sequence. And then finally there are display devices which could accept those signal in that form, and the device parses that signal and it displays the image based on the different kinds of technology. But in the digital domain, we can consider also in the same way we have digitized an analog signal. So we can perform the sampling and quantization, and then of course since it is a the corresponding information would be huge if we in the raw form, if we store it, corresponding requirement of the bits would be very huge for the digital domain. There will be a lot of samples, and per sample if you are using say 24 bits for a color representation, the size would be huge. So that's why we usually they are stored in a compressed format by using compression devices, and those are finally transmitted once again. And while transmitting also, sometimes we convert them into the analog signal and then we transmit it, or we can use any digital display devices to display it or store it, whatever is your purpose. But the other thing is that directly we can also capture digital images as we capture from today's CCD cameras or CMOS cameras. So there we have to capture directly, and then it becomes directly a digital image. And now following certain representations, some of the standards, we can represent it also as a sequence of frames, and then use that same compression and other technology, the same technology, for doing the other things. So this is more or less a very brief overview of video acquisition and different formats those are associated. I would give a bit more elaborations. So one should know that this in the since compression is a kind of necessity when you are going to use a video, mostly that particularly for the purpose of transmission and storage, and then there are different standards for compression. So depending upon the quality of videos that you require for different purposes, there is a compression called motion JPEG or MJPEG, which is simply almost independent compression of frames over the time series frames, compressed frames. Or even you can exploit the temporal correlations, not only the spatial correlations, by standards like MPEG 1 to 4, and for higher compressions you can have H.263 or H.264 for efficient compression, I should say, and also maintaining quality. And HV compression, that is also another high definition for high definition TV or frames or video frames. Some of the basic operations on the videos that we may consider: that shot detection, that means detecting the consecutive frames which are related to a particular event or particular view, I should say, of while capturing the video. Then feature extraction, as we discussed, feature extraction of images, standard still images. Similarly, features for videos are needed to be extracted for the purpose of, again, higher level processing like classification, clustering, etc. Then the tracking of objects, that's a kind of very, I should say, very active areas of research in video and active requirement. One of the major processing requirement for videos to track the objects over the frames, the same object which moves, how can I find out its locations and also its velocity over the videos. So process of conversion from analog to the digital form, again there are different methodology and different standards. So this is what is the analog video scanning. We want to perform the sampling of the signals, but how the signal is generated, that means, so when you are traversing a frame, so it's a time varying signal where, as I said, so every frame would be scanned over the two-dimensional image, so maybe row wise and then column wise scanning. So that kind of scanning. So we say horizontal and vertical scaling, and after completing the scan of one frame, then again we retrace back to the beginning of the next frame. So this is the kind of scanning we do, and finally we can generate a one-dimensional signal at a time, and as I mentioned, we can sample that signal at regular intervals of space, regular intervals of the coordinate points, and also the time. So this is the kind of things we do, and then so as you can see that from video is normally it's a three-dimensional. You can consider it as a three-dimensional entity, including space and time. or we can say that it's a two-dimensional spatial entity for an individual frame, and then there is a temporal entity for one dimension across the frame. So something some variables characterizing certain changes which we can provide the additional informations over time, and still it can give me back the sequence. So frames are temporal sampling is a 2D frames, and it is also spatial function, and this is a kind of digital form. And when we consider the analog video, we do the scanning signal in one dimension. So there are two types of scanning, particularly when we generate the video frames, and as it is closely linked with our television technology. So one kind of scan is progressive scan, where each horizontal lines are scanned, and then after the end of that frame, again you go back to the next frame to the same position, topmost and leftmost position, and again you start scanning from left to right. So this is called progressive. Whereas for interlaced scan, what we do that we perform the scanning, cover this zone very quickly by increasing the gap of horizontal scans. That means every even field, every even line is scanned in one go, and then again it retraced back, and then every odd line is scanned in the next row. We call them even line and odd line. So one scan is for these lines which are even lines, and the other kind of scan is for odd lines. So in this way you can make the video flicker free, but because you are quickly covering the whole scan, though it's coarse resolutions, but next again you are covering it. So it gives better visualization, but it's little as you can see involved while digitizing it and while representing it, because you have additional information of these divisions. We call them fields. There are two fields of frame, one for even frame, another for odd frame. So just a summary: progressive is scans a frame in every delta t seconds, that's the period of scanning, and then it performs the horizontal scanning, and then there is a retrace. That means it moves from one horizontal line to the next horizontal line. So it shows here from B to C transitions. So we can consider that when we are doing these things, it is basically this technology is developed over the principle of cathode rays tube scanning, and where electron beams are scanned through the sweeping signal. So accordingly, these are described in this version. And then D2A is the vertical trace. So in our digital processing, we may not go into much more, we may not consider those details of retracing, etc. We get the video data in the form of frames per frames over the time, and that sequence of frames, and then we process it. But just for your information, you should know that thing. And one typical example of the sampling interval is 1/72 seconds. So every second there are 72 frames. Similarly, the interlaced scan, where you have the division over the fields, even fields and odd fields. So these are the two divisions in a frame, and so in this case solid lines are odd field, rather solid lines started first and the dotted lines are even filled. So if I say F2A retrace, that is the retrace of vertical. So this is F2A. So it is a vertical retrace. Vertical trace would come after every field. That is after odd field. So after the frame. So again the next frame odd field will start. And dotted lines even filled. So there would be a D2A retrace. D2E retrace is this to this. This vertical retrace is for going to the next even field tracing. And then it is the purpose that to reduce the flickering in TV without extra transmission bandwidth, taking extra transmission bandwidth. So digital video, where directly we get the videos from the capture. So there are spatial digitizations. We say spatial digitizations is over the space, that is pixels in each frame per field. Okay, so this digitization is also from the analog signal. So horizontal and vertical resolutions. Then in each frame or field, it is not per, pixels in each frame or field, and we should note that how many pixels per horizontal line and how many frames over the sequence. So and what is the gap of the horizontal lines, how many lines per frame. So how many pixels per horizontal line and how many lines per frame. So that is the kind of specification of horizontal and vertical resolution. So and the aspect ratio is also considered. There are different standards. There are some standards. So 16:9 is for HDTV aspect ratio. For temporal digitization, once again the parameter is that what is the frames per second, number of frames per second, typically 50 to 60 hertz, that is the frames per second. So 50 fields per second of interlaced fields. So if I say 50i, so 50 fields per second of interlaced fields means actually 25 frames per second. But 60 progressive frames per second, 60p, which means actually 60 frames per second. So we can see that these two rates are different, and 60p is much higher rate than 50i. And these are some typical figures of different kinds of video format, and they describe different resolutions of those format. You can see here the size of the video, that is the 720 into 488, which is 720 is the number of pixels per line and 488 is the number of lines per frame. So this is that HD video standard. For HD video standard is 1280 into 720, full HD is 1920 into 1080, and ultra HD is 3840 into 2160. You can also see the relative size of the aspect ratios. So advantage is that in the digital video that you can directly process it. If you have the digital video in this format, you can directly, so you can store them conveniently, you can compress them, and then the error-free transmission is possible. You can do encryption. So there are several advantages, some of them directly from the digitizations, and as such for the video standard itself. So different format I have just mentioned about the size, but now there are other related major informations are given. Say for example, VGA video has a 4:3 aspect ratio with 640 into 480 frame size. WXGA has 16:9 aspect ratio, and HDTV is that 2:1 interlaced, it is there. So in this way, even the pixels are also, lines are also stored in that fashion. So interlaced fashion, 2:1. So every two lines, say in the first field, there is only one line for the second field. And as you can see that it means that there are three lines, first two, so one of them, out of the three lines, two would be sent in one go, and other one would be sent next door. So this is the understanding here, and this is how we interpret. Similarly, 2:1 interlaced and 25 hertz for HDTV, another standard. So the variations are mentioned here. High definition TV, we have 1280 to 720 is the frame size. Then it's a progressive video, and it could be 50 or 6 to 60 hertz of frame rate. Full high definition has this, and it is an interlaced, once again interlaced video standard, and 25 to 30 hertz. 25 and 30 hertz, there are two typical frame rates. As you can see, this is slower than this high definition TV here. Another full HD standard 9, it is a progressive difference, it's a progressive. Frame rate is not mentioned, so usually it should be in that range, 50 to 60 hertz. So for some of the cases of lower end users, we have ranges even as from very low quality to a moderate quality video, and we call them QCIF or common intermediate format. CIF is common intermediate format, that is standard 352 into 288 and 30 frames per second, and this is the chroma part, 4:2:0, that is a chroma sampling. I will explain it later on. So if it is CIF, so 1/4 of size is called quarter CIF. You can see from the respective size of width and height, everything has been reduced by half. So that makes the quarter of the total size. Then source input format SIF, it has both 352 into 288 or 352 into 240. Here the frame rate could be of two different frame rates is there, and 4 CIF, so 4 times of the CIF format. So you have this particular standard. Then 16 CIF has much larger standard. So larger frame size. So these are different kinds of standard on which the videos are defined. Digital videos are defined. So now let us come to that color representation or in video, in digital video. And as we know that color pixels could be represented by in the usual way they are captured in red, green, blue. But again they can be transformed into any other color space. Even the linear transformation is also there. So there are luminance and chroma part can be separated out from that transformation. So we have this CR and CB, YCR CB or YCB CR space for the color representation digital video. For analog representation, there is a standard, there is a transformation called U and V, YU and V transformation. That is for analog. So, so this is just an example that how CRCB, when it is normalized representation, how the colors are represented. It varies from -1 to 1. Each one is varying from -1 to 1. So you have this particular conversion matrix, which is same as the YCRCB transformation, and we have seen that already. There is a translation. So it varies from actually from say 0 to 240. This two in this case. So this is some example that the same color frame where you are component, this is the luminance part and these are the two chroma part. That means CR complementary red and complementary blue part. Just an example which has been shown here. For subsampling the chroma part, we have seen for compression, particularly in JPEG compressions, there are different subsampling schemes because chromatic information requires less bandwidth. That is why you can subsample them. So subsampling schemes are described in this fashion. Suppose you have a 4 pixels width, say in a row. If I consider there are 4 pixels, say in a row, and then B is the number of samples of color pixels in row 1. So A is the 4 pixels, so naturally luminance would be there in every pixel. So B is the A is to B is to C. So B is the number of samples. So suppose if I say there are row 1 and row 2. So you have to take 2 consecutive rows. So this is the total number of say pixels, say 8 we are taking, and then B is the number of samples. So if say B is 2, suppose I am giving 4 is to 2 is to 1. So what we will do, we will consider say this 2 are having the chroma information, both CR and CB information would be available there. But on the second row, this is for the second row. So for the second row, for this 4, for this 4, we have only 1 in the row 2. You have only say this is the information. So this is how this is the 4 is to 2 is to 1. That means full color. So again, if you repeat it, so it will be going like this only. Say if I repeat the next 4 in the same row, so there also we will have say these 2 are chroma and information and this is the other. So in this way the sampling takes place. So this is to reduce the, as I say, the size of the data itself. So there are several such schemes which are used here. Say 4 is to 4 is to 4, each pixel having all the color information, and you can consider other schemes as I explained. Particularly you note this scheme which is very popular in JPEG standard also. So it says that 4 is to 2 is to 0, which means each pixel Why in alternate row, every alternate pixel contains the color information. So, if I pictorially show these things, I mean, as I mentioned, this scheme particularly most commonly used reduces most, and also it reduces the image size by approximately 17%. So, if I pictorially show this sampling, just know this is what for 4:4:4 you can look for every pixel it has associated chroma. But on the other hand, in this case it is 4:2:2, which means that every row has this 2 chroma information, 2 chroma, even the first row and second row. So, this is the 4:2:2. This is 4:2:0. So, you have now every row you have only 2 chroma information. So, we can say this is the, it shows like that, say this is chroma information and this is the chroma information. Actually, in other way you can say every 2x2 block has 1 chroma information. That is also another way of putting it. This is 4:1:1 and this is 4:1:0. So, this is a chroma format for sampling the chromatic information. So, let us understand the requirement of bit rate and also the we can say that associated with bandwidth, which means the bit per second. So, as we see, just a simple computation, a typical cases, say in a typical case the pixels size, say consider 640 into 480, then frames per second, say 25 frames per second, bits per pixel, so raw videos we say 24 bits per pixel, and say duration is 1 hour, which is 3600 seconds. So, if I just apply simple arithmetic of multiplying all those factors for every frame, every second, how many bits, how many pixels we are generating. So, for this video, how many pixels are generating for 1 hour video, you can see these are the total number, and finally resolution is so many pixels, bits per frame, so many bits per frame, and bit rate is this 184.2 Mbps, megabyte bit per second, and video size would be, for 1 hour video it would be 82.8 gigabytes. So, it is a huge requirement. So, that is why compression is a necessity when you are considering capturing or storing a video. So, huge bandwidth requirement for transmission and space requirement for storage. So, we need compression. So, let us now have a brief overview of video compression, and we will be considering particularly a standard H.264. We will give overview of that standard. Actually, in a video compression there are different kinds of redundancy that is removed through the processing. Those redundancies are taken care of through series of processing. So, there are perceptual redundancy removal where we do not require that much of higher sampling rate for the chroma. So, chroma subsampling could be there. Quantization, as you understand that our visual system itself, it cannot distinguishes beyond certain resolution of the numeric representation of the values. Then we can perform pre-filtering by reducing the bandwidth, because our system also works on a particularly, these are all band limited systems. So, we can consider those bands that should be only taken care of or representing the signals, and sometimes the object extraction. So, it is a kind of saliency. So, we are our attention is mostly drawn to some of the objects, and what we do that we try to represent those objects in a much more detailed way compared to other objects which are not to be in our field of attention. So, there are different such things that we can do for removing the perceptual redundancy. For spatial redundancy removal, so as you understand, this is basically the intersampling similarities, and there are different kinds of transforms which takes care of this part. Say discrete cosine transform is widely used for removing the spatial redundancy, and integer cosine transform is also there is another option which is computation which is efficient because of use of integer arithmetics. Then we can predict the corresponding blocks from one block to the other blocks, or you can also make the block size different. So and for different block size transformation you can use. What we do actually when we perform discrete cosine transform, we perform over a block, say either 8 cross 8 or 16 cross 16 block, and then that in the standard we use that particular block. Now depending upon the objects, depending upon the details that is there in the frame, and also in the region what is going to be represented, how much details is there in the regions, this block size could be varied. It could be larger block, so larger the block, better is the compression. So but the problem is that in that case we may lose many details. So there is a trade-off. So that's why this adaptiveness could be there for variable block size transformation. Then the third thing, redundancy is of type temporal redundancy. So it's a correlation between the frames in consecutive time instances. Almost similar information is there. Mostly, say if you have the motion related information, then from that motion information you can derive predict the next frame from the previous frame, and whatever little bit of difference is there you can encode them. So one of the major computation here is that the estimation of these motion vectors, by which every block how it moves, what is the direction of its movement to the next frame, where it looks almost similar. And there also the block size is important, so there could be variable block sizes. And when you are estimating also, instead of considering only previous frame for prediction, because video could be encoded offline, it is not real time transmission always. So you can store it in a buffer for a certain time, and you can make the transmission as buffered, delayed transmission. There could be some latency in video transmission. So considering that, you can have multiple reference frame while doing the motion estimation, and you can improve the efficiency of predictions. And finally, as you know that it's a representing information. So what is the efficient way of representing information? So that distribution, statistical distribution of occurrences of certain values are say more probable than the other. So then what we can do variable bit encoding of different values. And there are several strategies like Huffman coding, adaptive variable encoding, arithmetic coding. So these are several things we call them entropy coding or statistical redundancy removal techniques. So these are the four in the pipeline. These are the four stages by which a video could be compressed. So while performing this compression, so these are certain concepts to be used, or the structure has to be some structure has to be standardized, and based on that structure this compression should be compression scheme should be implemented. So as we understand that when you are doing this kind of predictions, so certain group of pictures are to be put together, which is the consecutive set of frames. So certain length of sequence that needs to be considered. That is the GOP or group of pictures, not only frames with the sequence. And then there are frames which are to be compressed. We call also slice. So it is basically a part of the frame, certain lines of the frames or certain intervals. That means pixel locations from one pixel to the another pixel. And in certain order, these frames are to be scanned. So these blocks are to be scanned either say row wise or column wise or the other one, or it could be of different scanning. Then there are the size of the block, and we call it macro block. A group of blocks could be also put together. So these are certain things that one need to specify as a part of the organization of a compressed data. And this exploitation of redundancy, as I mentioned, that for spatial redundancy removal, intra-frame coding, that means within the frame, like the image compression, we can do those encoding there itself. And for temporal, it is inter-frame coding, that means the information related to the consecutive sequence of frames. Then the motion estimation is one of the major component of temporal, one of the major tasks while removing the temporal redundancy, because by computing motions of this block, we can have one block that where it goes. Motion is basically motion of a block from one frame to the other frame. So if I know the motion vector, that means offsets, so I can simply use that offset to predict the values of that block from the previous block. So that is the advantage we have, and that's why motion estimation is used, and this is called motion vector. This offset is called motion vector. It is a displacement between the current block and the reference block. And what we need to transmit in that case, we transmit simply the motion vector, and then we consider the difference to make it more, less to make it more robust, and also to provide you the exact information, almost same information of the block or the loss. To minimize the loss, what we do, that we transfer the motion vector, reference frame, and the difference between current block and reference block. So these are the three things: the motion vector, reference frame. Sometimes reference frame by default may be the previous frame, we may not transmit, or we can transmit through encoded form. But as I mentioned, that this reference frame could be also a group of frames. Then while performing motion estimations, we have to consider several different types of matching algorithms, so that we have to find, that is a major computation, we have to find the closest match block in the spatial and temporal neighborhood. That is the primary task, and once we find out the closest match block, then the offsets of the positions can give you the motion vector. Usually in the motion vector we consider only translatory motion, that is mostly followed in the videos. So there are different nomenclatures also. As you see, intra-frame is denoted by I, or we call it simply I frame. Then the P frames are the frames predicted from intra-frames, and B frames are the frames predicted from actually bidirectionally predicted frames, and P is a unidirectionally predicted frame. So P is predicted from intra-frames. So as we are showing, I is intra-coded frame, predicted coded frame, B is bidirectionally predicted coded frames. So as you can see, the P will be from intra-frame or from its previous predicted frame, and whereas a B frame could be predicted from both from the past frame and also from the future frame in that sense. So this is, and they are predicted only from P or I frames. So this is, and I frame also in this structure, as you see that this is typically a GOP description, and this is a GOP structure. So this sequence in a GOP, this is a sequence. So since if we store the video, and while moving, considering fast forwarding of a video, what we can do, we can simply display the iframe. So that becomes a fast forwarding operations. For intra-frame predictions, let me give you a brief overview of different prediction modes or standards. One is that intra 16x16 blocks by different kinds of scanning. Say if you do vertical scanning, so you are predicting the pixels here, say from these past pixels. That is the kind of modes here, 16x16, or in horizontal you are predicting in the horizontal scanning. In this way you can predict. This mode is simply DC mode. So you are just simply predicting the mean of horizontal and vertical. So mean of horizontal and vertical, use the mean and horizontal and vertical to predict it. And another mode is plane mode. You can see it traces in the diagonal directions. Whereas intra 4x4, it has 9 modes. So there are 8 directions here. So 0, 1, and then So just to show you that 0 is the vertical, so this direction shows vertical direction predictions. Then 1 is horizontal, then 2 is DC prediction, that is mean, using the mean of horizontal and vertical scanning. ABCD is scanned in this way. This is the direction of prediction. So prediction is that in this scanning, the past pixels or the pixels which are appearing before the others, they are used for predicting the other pixels. So these are the things used for this case, and this is the other mode. It is explained. And whereas IPCM is directly encode values, which means we do not use any prediction. So there are different kinds of interframe prediction mode. So while transmitting any particular predicted encoded structure, so there we first need to transmit the mode information and followed by these particular predicted structures. For motion estimation, as we have mentioned, that we need to compute the block which is similar. So this is the frame at time instance t1, this is one frame, and this is the second frame at time instance t2, and say this block we want to predict where this block what is this block. So actually we do the other way. We consider, say this block is moved here. So for each block we find out from which block it came. So we code the respective position and position in the previous frame, that is the location and with the frame, and also the respective difference and the motion vector. And the motion vector, that means say this is the motion vector, and that would give me the position. So this position would be giving me this motion vector, or this motion vector, if I compute, that would give me the position. Actually that is what we do, and then after that what we code, we encode the error between those two informations. So if I encode the error, so with the predicted block, so from this block, by moving it by this offset, I can get a rough estimate and then add the error to get the full image, to get the more closer image information. So this is what the point xy in psi1 moved to x plus dx y plus dy, and then this is the motion vector dx dy. So motion estimation types could be, as I said, that if t1 is less than t2, it's a forward motion estimation, otherwise it's a backward motion estimation. These are certain things. As I mentioned that using motion compensation, motion vector, first you get a rough estimate of the frame. So use this vector, you use the motion vectors, use the past or use the reference frame, then you can get the motion compensated frame by forming these respective blocks, and then you get the residuals which are computed, which are also transmitted during completion. So residuals are computed from this one. So we consider the block which is closest to this block, right? We compute the block which is closest to this block, this psi1, so that needs to be considered. So argmin of psi1 t1 over these motion vectors, that gives you the corresponding motion search. And this is the error what we use for optimizing, or what we use for computing this similar motion blocks. So exactly what we are doing, suppose you have a frame and consider this frame you are encoding and there are blocks. So you have partitioned these blocks. So for these blocks, say suppose this is for T2, and suppose there is another image at T1, and take this block and find out which block in T1 which is closely similar to it, and for that you use this error function. That means you take the norm of their difference. So each pixel wise difference, raise it to the power p. So for the case of L2 norm, this p is equal to 2, and you compute what is the value of D. So around this neighborhood, so there is a search space. So instead of searching every point in the image, because that would be that would take a lot of time. So you search only around the neighborhood of this one. So maybe since it is the boundary, say maybe you define this neighborhood search point area and consider every possible location, and you find out where this error is minimum. So take that location as the closest match to one, and you use this location to define these motion vectors. So while transmission, you transmit this frame ID and also this motion vector. So from this ID, using that motion vector, you can get an estimate. You can get an estimate of this information, and as you have also transmitted the residual, so from the residual you can just add that residual, and then you get a very close estimate of the actual what was there originally in that block. So this is how the motion compensation is done. So for this actually there are different block sizes are considered. So we can have different kinds of flexible partitioning. As you understand that if the object size is large, then we can have larger motion block, macro block size, and with the rigid bar, just simple translatory motions. But when there are a lot of smaller objects which are moving, then we need smaller block sizes. So that's why instead of going for any fixed partitioning, we may go for flexible partitioning. But when you are doing for flexible partitioning, then you have to again provide those information to identify that which partitioning scheme you are following. So similarly, so these are the several options are available. Like you can have 16 cross 16 block size, block partitioning, and out of this 16 cross 16, there are 4 different kind of partitions. So you can use full 16 cross 16 for the computing motion vectors, or divide it into 2 vertical, split it into 2 vertical blocks and compute motion vectors for each of them, or make it horizontal split, or make it 4 cross 4, 2 cross 2 split. So for each one you will have so many motion vectors. So for this one you require only 1 motion vector. For this one you require 2 motion vectors. For this one also 2. For this one also 4. But it depends. Sometimes because you will lose also information if you don't do it, or your error would be also very large. So effectively your compression will not be that much. You can do it the same thing for 8 cross 8 also, similar partitioning scheme. Or sometimes you may not compute a motion vector if you find there is almost no change in the same position itself. So we call it skip mode. That means we just repeat whatever is there in the previous reference frame, we just repeat it there. That is the skip mode. So for that you don't transmit any motion vector or residual block, because only thing is that reference frame has to be there, so which has been transmitted. So that from the reference frame you can again reconstruct the information there. In another mode, MV is predicted from neighboring motion blocks, macro blocks also. I have discussed about briefly motion search while doing block matching, where this LP norm, that means L2 norm I have mentioned. So it could be exhaustive search, that means each and every pixel of the neighborhood zone you have to search, or it could be reduced neighborhood search. So just to explain, say this is your target block or current frame, and say this is the block, these are the split, this is the partition of the blocks, and say these blocks for which you are going to do motion estimation from a reference block. Say this is the reference block. So in the reference block, now you consider this position, and around this position, since this is a block location, so around this location you consider the neighborhood locations only. Among these neighbors, each and every location you search with the same block size, and you compute the error. Say you consider this location, say this is the block, so you compute the error between these two, say L2 norm between these two locations, and you get some value, and you can come search and find out the location where it is minimum and take that location. So this is called exhaustive search for block matching, though you are using certain neighborhood size, and that is the parameter only. But you can do reduced neighborhood search, which means that you need not do for every sample. What you can do, you can search, or you can reduce the size of the neighborhood also, and you can search for that. Or you can do fractional pixel accuracy, which means even the motion vector here, the motion is discrete in terms of the discrete pixel locations only. But what about if the motion is a fractional pixel locations? So even you can make your search more precise by interpolating the frames and taking account of that fractional movement. You can have bidirectional motion vector. That means instead of one reference frame, you can have two reference frame, one past, one ahead of it, and from the same locations you can get say two motion vectors and improve your search. So you can have multiple reference frames. So there are different strategies that you can adopt in this case. Use the weighted average from each one of them, motion predictions. So one typical example is shown here. So here the leftmost topmost is the current frame, and rightmost topmost is the reference frame. So that is the block, and you can see that reference frame. So these are the frames, and you can see at each locations you can find out what is the motions. So if I consider each location is showing a kind of block location because it's subsample location, and it gives you the motion. So if I say this location is this, so this is I should say current frame, actually say this one, this location, and since this motion vector is this one, so I will search the point here, for example, something like that. So those are the motion vectors. Then motion compensate. So this is the motion compensated image. So the quality, of course, it does not look good here, but that is what you get in this case. So the next thing what I would like to discuss is that the short detection in a video. So let us first try to understand what is meant by a video short. A short is a set of consecutive frames of a video, and it is maximal continuous partition of video sequence in temporal domain. So which means that if I have the sequence of frames, and let me write it like a movie film, show it like a movie film structurally. So maybe a short is one such segment where as if you have taken that images from the same imaging I should say parameters or imaging configuration of a camera. So you have a video camera, so you consider sports video. So there are say multiple say video cameras, and from this video you have taken certain portions. From this video camera you have taken another portion. So we call this is one shot from this one view from this, and this is these images are from another view. But when you are composing this video, you are basically concatenating them, and they are available in the same videos. This is just one simple example. Even this single camera also, with the movement of camera, you can create different shots at that particular time instances or time interval. So it is the maximum continuous partition of video sequence in temporal domain, which describes the similar kinds of events in this case. And then without any interruption, that means which is a smooth description of certain story. Then it is also a single capture device. So it has to be captured by a single device like camera. But when we are doing say video compression, we use a group of picture concept, and which is usually fixed length syntactical segments. That means in a GOP there could be again a boundary. GOP may contain boundary of two shots or boundary of multiple shots, boundaries of multiple shots. So GOP does not define a shot. GOP is simply a syntax for parsing a video from its compressed format. But short could be of variable lengths, it's not fixed length, and each short has certain semantics associated with. So what is the event going on at that point of time with a continuous time instances? Temporally they are very much correlated and continuous. So today we will stop here. We will continue this discussion. Just a brief definition of short that we at the end we have provided. But what are the algorithms for short detection that we will discuss in the next lecture. So let me stop here today and thank you very much for your patience and listening.